Okay. So, we were discussing MMSE estimate, right. First of all we said, so we defined the conditional expectation, expectation of y given x. We defined this as a random variable which is measurable under the sigma algebra sigma x, right. So, I mean in more plain language, expectation of y given x is a random variable which only depends on x, right. To say it a little more mathematically precisely, it is a sigma x measurable random variable, right. So, we call this some psi of x, right, and we said that. So, we define this only for the case when x and y are discrete and for the case when x and y have a joint PDF, the case when x and y are jointly continuous, right. Only in those two cases we could define this in terms of an expectation with respect to the conditional density or the conditional PMF, and then blindly replace the actual value with the random variable, right. That is how we defined it. It is somewhat it is a very elementary way of defining it, and we said that. So, we said iterated expectation holds. So, this is the law of iterated expectation. So, we said expectation of y given x equal to expectation of y. So, this we proved again by explicitly writing it out for the case of discrete and jointly continuous random variables, and for I also said for any, so we said also for any measurable g, well any measurable g, we said expectation of y minus psi of x times g of x equal to 0, right. Right, this is what we said last time, and this again you can show by explicitly writing it out whenever this is defined, right. Expectation, another way of saying it is expectation of y g x is same as expectation of g of x times the conditional expectation. Okay. Now, this result we interpreted geometrically, right. We said that you can view psi of x as an estimate of y that only depends on x, right. Suppose x and y are some dependent random variables and you want to estimate y, but you cannot observe y, right. Let us say you can only observe x and you want to somehow come up with an estimate for y, all right. So, if you view this as an estimate, the expectation of y given x as a random variable which estimates y only based on x, then y minus psi of x represents your estimation error, right. So, what this is saying is that in this estimation error is orthogonal to any function of what you observe, correct. So, we already established that these square integrable random variables are a Hilbert space, right. So, and the covariance plays the role of the inner product, right. So, in that sense we have I just drew a picture that said if you are looking at the subspace of sigma x measurable random variables. So, this whole space I am drawing it like R2, but it is actually the space of the Hilbert space of square integrable random variables. In that sigma x measurable random variables form a subspace of the Hilbert space, and what you are saying is that if your random variable y is some point here and you have to estimate y based only on things in this subspace, right. So, if you have to pick a sigma x measurable random variable which is the best estimate of your y geometrically it seems clear that you should pick the foot of the perpendicular, right, and this foot of the perpendicular is really what your conditional expectation is. So, that y minus I of x, which is your estimation error, is orthogonal to the space of is the subspace of sigma x measurable random variables. Okay. Is that clear? So, that is the interpretation we gave. Now, so this is something this is a result you can prove explicitly by writing it out for the case of discrete random variables and jointly continuous random variables. But for more general cases where x and y may be anything, right, where mixtures or singulars or whatever, we did not even define the conditional expectation, right, we do not know how to define it. In fact, this is taken as the definition of conditional expectation in the general case. Okay. So, you can actually prove that for any two random variables x and y and any measurable function g, there exists a random variable which is sigma x measurable such that this error is orthogonal to any function of x. Okay. The existence of such a random variable can be proven, and such a random variable can be shown to be unique except for a set of measure 0. Okay. So, this conditional expectation exists uniquely in an almost sure sense, right. Okay. So, that existence can be proved. Okay. That is how you define conditional expectation in a more general setting. This is taken as a defining equation. Okay. Is that clear? So, now and then we also said that psi of x is an Mmse estimate of y, that is for any function h we have expectation of y minus psi of x squared is less than or equal to expectation of y minus h of x squared. Okay. So, if you have any h of x will be a sigma x measurable random variable, right, it will be some random variable in that subspace, correct. Now, what we are saying is that for any random variable on that subspace, the error y minus the squared error, the mean squared error, this is called, right, the expected squared error is smallest when you choose this particular psi of x. Okay. And that is again fairly clear because of this orthogonal interpretation, right. I mean, if this were a normal Euclidean space, this is not a Euclidean space, this is a Hilbert space. If it is a normal Euclidean space, you would obviously choose the foot of the perpendicular as your closest point, and that intuition holds perfectly, right. And therefore, the psi of x is called the minimum mean squared error estimate, Mmse estimate. Okay. How do you prove this? So, I am going to prove it like this. I am going to write expectation of y minus h of x squared is equal to expectation of y minus psi of x squared plus expectation of psi of x minus h of x plus so I am going to write this as, so I am just trying to decompose this, right. I am going to write this as y minus I x plus psi minus h x. So, I should have a twice expectation of, what would I have, y minus psi x times psi x minus h x. Correct. Fine. Now, what can you say? So, you agree with this equation? Alright. So, I am just, this is just algebra, right. I am just expanding everything out. I hope I have not made a mistake. So, now if you look at this term, right, it looks like, so you can consider this as a function of x, right, this is some g x, right. So, what you will have is this whole thing is what, 0, right. So, this term is 0, you see why, because of that property, correct, and this term is obviously non negative, right. So, this must be greater than or equal to that. That clear? So, if you look at this, so if you just look at this, so this term is 0, right. So, what this is saying is expected y minus h x squared is equal to expected y minus psi x square plus psi x minus h x square, which is simply Pythagoras theorem, right, in this space, right. All right. So, this result follows. Okay. So, what, so this proof is using this fact, which again you prove using your elementary definition for discrete and jointly continuous random variables. But what you can show, see, in more generality, what you can show is that, I mean, you cannot, so this is taken as some kind of a defining property, right, this is taken as a defining property, and you have to show that such a psi x exists uniquely up to a set of measure 0, right. So, what you have is that in more general settings, this is not, I mean, this is not something you have to worry about too much, but let me just tell you that if you just consider expected y minus let me say y minus z squared, and I take infimum over all z which are sigma x measurable. Okay. So, I am considering that, so z is simply some parameter. So, z is a random variable which lies in that subspace, okay, and I am looking for that particular z which infimizes expected y minus z whole square, square error from this is a squared error from y. Okay. Now, this infimum is well defined. Now, the point is that this infimum is attained. Okay. The reason that this infimum is attained is because this being a subspace of a Hilbert space, Hilbert spaces are continuous, right, I mean to say complete, right, Hilbert spaces are complete. So, the space does not have any holes, right. So, there must exist a z which satisfies, which actually achieves this infimum, okay, and that infimum is your conditional expectation, okay, and that infimum obviously satisfies this, right, by just algebra, and that is how you define it in a more general setting, at least in L2 spaces, that is how you define it. Okay. Is that clear? So, I said I will briefly indicate how you define conditional expectation in a more general setting, right, which is exactly what I have done now, right. So, this set, so this infimum is attained for some sigma x measurable random variable, and that it is attained because the space is a complete space, being a Hilbert space, and that z is called the conditional expectation, and it is unique up to a set of measure 0. Okay. That clear? Are there any questions? So, this concludes our study of conditional expectations. Okay, so next we move on to the next module or next section on transforms. So, we will study 3 types of transforms. We will study actually we will first study probability generating functions, probability generating function or PGF. We have moment generating function, and we will study, probably in most detail, we will study the characteristic function. So, good references for this will be Grimmett and Sturzaker chapter 5 and OpenCourseware lecture 14 and 17, lectures 14th and 17th. Okay. And of course, I will upload notes. Okay. So, these transform techniques are at some level, you can think of them as some frequency domain techniques, just like in your signals and systems you have your time domain techniques, your frequency domain techniques. So, you can think of all your PDFs and PMFs as some kind of time domain functions, and these transforms as some frequency domain functions. Okay. So, that is a rough level of analogy. So, your knowledge of signals and systems will come in handy in this particular section. Okay. So, this probability generating function, which is commonly used for discrete random variables, particularly integer valued random variables. This is akin to your Z transform for your discrete time signals, right. And moment generating function is similar to Laplace transform, okay, and characteristic function is similar to Fourier transform. Okay. In some rough sense, we will see. Okay, we will see properly. So, these transform techniques are very useful in a number of settings. So, sometimes they help their simple one simple use is that sometimes they help you compute things much easier, right. Just like for example, if you have to convolve densities or convolve PMFs, it is much easier to go to the in your signal system, you go to the frequency domain, multiply, invert your transform back, right. So, those sort of computationally they are useful, and they also are very useful in analyzing certain stochastic processes like branching processes, random walks. They are useful in proving limit theorems such as the central limit theorem, strong law of large numbers and so on, law of large numbers and so on. Okay, so, they have a number of uses. Okay. So, let us deal with probability generating functions. Let x be a x be an integer valued random variable, define g x of, so you can define the g x of z is equal to expectation of z power x. Okay, that is the definition of the probability generating function. Okay. So, this is an integer valued random variable. So, this is, you can just write this as sum over I z power I probability that x is equal to y. Okay. So, z is just some parameter. Okay, you can think of z as, generally this z could be some complex number. Okay. So, what you are looking at is some summation of a complex series. Okay. And this looks like, so if you were to look at this guy as some kind of a discrete time signal, this looks very much like your z transform, except usually you have a minus here for the z transform, but otherwise it is analogous at least. Okay. And you sum over all I. Okay. Now, of course, there is, when you write down a series like this, there will be all sorts of questions on whether the series converges, what kind of convergence does it, it is a complex series after all, right. So, you have to talk about what the region of convergence is, whether does it converges absolutely uniformly and so on, right. So, so these convergence issues we will push under the rug a little bit for this course, okay, because it requires it requires some knowledge of complex analysis. Okay. You already know, I guess, that from your study of signals and systems, you know that Z transforms, the convergence regions are what kind of figures? They are generally annular, they are circles, right. In general, circles are annular regions. Then that is true here. Okay. It's there exists some radius of convergence. Okay. So, let me just mention that. So, convergence so there exists R, so this could be possibly infinite, such that the PGF what I mean by PGF converges is that the series converges, right. This PGF converges for all z such that absolute value of z less than r and diverges for absolute z greater than r. Okay. Actually, I think this particular statement is so I am missing out a little bit here. I think this statement is probably true for non-negative valued random variables, right. Otherwise, you could have these z power minus I terms and you may have annular regions of convergence. So, if this statement, I believe this statement, let me clarify this, but I think the statement is true for non-negative integer valued random variables, right. Let me clarify this once I confirm this. The one thing you can say for sure, so this R may be infinity also, in which means that the series converges in all in the whole complex plane. Okay. The one thing you can say for sure though is that this radius of convergence includes z equal to 1 for sure, right, because you will simply have, so if you have z equals 1, right, or z absolute z is equal to 1, then you will certainly have absolute g z is equal to absolute value of that, which is less than or equal to absolute value of so you will just have 1, right. So, for z equal to 1 you have absolute convergence and therefore uniform convergence, right. So, this region of convergence will certainly include the unit circle, right, whatever else it includes or not, it does certainly include the unit circle, correct, this region of convergence. I mean normally if this were some arbitrary discrete time signal, that is not necessarily the case, but because this is a PMF, your region of convergence will include the unit circle, right. So, that much is clear, and whenever, so if you are in the region of convergence, you will have absolute convergence and therefore uniform convergence, okay, and therefore this PGF will be well defined. So, and that is as much as I am going to say about convergence issues. Okay. So, I mean I am not going to dwell on this too much because we are mostly going to use it as a tool rather than worry about its existence and so on, right, existence, analyticity, you can talk about all sorts of stuff for this complex function, but we will use it mostly as a computational tool. Okay. So, I will not dwell on this convergence issues too much. Okay. I will confirm this statement's correctness. I am pretty sure it holds for non-negative random variables. I will confirm this. So, let us do an example. Let probability of x is equal to I is equal to e power minus lambda power I by I factorial, I equal to 0. So, Poisson random variable, here your g x of z will be sum over I equals 0 to infinity right. And that is simply the series for e power lambda z, right. So, this will become e power lambda z minus 1, okay. And that is an analytic function in all of the complex plane, right, it converges uniformly, it is analytic in the whole complex plane. Okay. So, this is for any z in C. On the other hand, if you try doing this for geometric, so if you have p x is equal to I is equal to 1 minus p power I minus 1 times p, then you will get g x of z is sum over I equals 1 through infinity 1 minus p z whole power I times p, isn't it. So, that is equal to p z over 1 minus z times, so sorry 1 minus p times z, and that holds for absolute value of z less than 1 over 1 minus p, correct. So, that is your radius of convergence or region of convergence. It clearly includes absolute z equal to 1, right, it always includes absolute z equal to 1, it is a little bit bigger than that and depends on p, okay. And out for z bigger than that it does not exist, okay. Is that okay? So, in terms of notation I am using big G for generating function, okay, and x I am suffixing it with the random variable I am talking about, okay, and z is the argument. So, let us look at some properties. First property is that if you take dg dz and evaluate it at z equal to 1, you get expectation of well, okay. So, the maybe the property 0 should be that g x of 1 is equal to property g x of 1 is equal to 1 always, right. You can see in these cases as well, right. G x of 1 is 1. I am saying that g prime of 1 is equal to the expectation of x. So, if you know the probability density function, you differentiate it with respect to z and set z equal to 1, you get the expectation of x. So, what is the reason that this is true? First of all, is does this derivative always exist? See, the region of convergence always includes, you see it always includes the circle, the unit circle absolute z equal to 1, right. So, in that case you will have an analytic function which you can differentiate, and you can just set z equal to 1, right. So, the way of proving this is that, so you are differentiating this, right, if you are differentiating this series essentially, and you will get I z power I minus 1, right, and you are setting z equal to 1, right, and you get I times p x equal to I. So, which is the expectation, right. The only thing that I mean, again I am not being very precise about is that how you can take the derivative inside the summation and things like that, right. If it is a finite summation you can do it, but so basically you are, it is justified when the summation converges to an analytic function, then you can take the derivative inside the sum. Okay. I am just pushing those details under the rug a little bit. Okay. And you can show that the kth derivative, similarly you can show that the kth derivative at z equal to 1 will give you expectation of x times x minus 1 times x minus k plus 1. Right, similar argument you can prove that. Okay. Similarly, analyticity at, and if analyticity on the unit circle will imply this result, right. Third, if x and y are independent and z equal to x plus y, then g z, well, okay, so now I have to be careful. So let me call this something else then, right. X plus y is equal to some other random variable. What shall I call it? Or let me just call it z and just call g z of s, let us say, right. So, I mean I do not want confusion between the argument and the random variable. G z of s is equal to g x of s times g y of s. Okay, so, you can multiply the, so if x and y are independent, z is the sum of the two, just like so if x and y are independent, then you will the discrete random variables. So, you will convolve their PMFs, but convolving your PMFs is same as multiplying your PGFs, just like in your discrete, if you have discrete time signals that are convolving, you multiply the Z transforms, right. This is the same result. I am writing S here just to avoid confusion with the random variable itself, and the region of convergence will be the region where both converge, intersection of the regions of the convergence. So, if you want to show that sum of two Poisson random variables is independent Poisson random variables is a Poisson random variable, you can just directly look at this, right. If one of them has parameter lambda, the other has parameter mu, then you can show that the product will have parameter lambda plus mu. So, it is a Poisson with parameter lambda plus mu. So, in one shot you will get it without convolving and whatever, right, you get it. And obviously, this extends to n independent random variables also, you just multiply the PGFs. So, if you want to find the PGF of a binomial random variable, you can take the essentially take the nth power of the Bernoulli PGF, right, because binomial is sum of Bernoullis, right. Yeah, so this is very useful. Okay. So, we in your last quiz you had this problem on the negative binomial, right. So, you try as an exercise, perhaps you want to try finding the PGF of the negative binomial and then proving that the sum of those two negative binomials is another negative binomial, right. That is something you proved the hard way, I guess, but you can prove it easier using PGFs. Okay. So, the last property I will talk about here, property number 4, is about a random sum of. So, let us say z is equal to sum over I equals 1 through n x I, right, where x i's are IID discrete random variables, actually in positive integer valued random variables, let us say, and n is independent of x i's. So, in this case you can show that g z of s, you can denote by z n, z big N if you like. Okay. So, g z of s is equal to g n of g x of s. Okay, so, if you want to find the PGF of this random sum of random variables, right. So, you compose the PGF of n and the PGF of s. Okay. And how do you prove that? You use iterated expectations. Okay. So, you have g z of s is equal to expectation of s power z, right. That is, you write this as expectation of s power z given n. Okay. This is by iterated expectations, right. And so, if you fix an n, so you can compute this, right, expectation of s power z given n. So, if you are fixing an n, expectation of s power z will simply be the n time product of g x, right, because if you fix n equal to little n, this will simply become I is equal to 1 to little n x I, and the PGF of that we know, simply g x of s raised to the nth power, right. So, but if you replace small n with capital N, this will simply become expectation of g x of s power big N, no, right, I am skipping a step, okay, and this looks like what you want, right, this is simply g n of g x of s. Okay. You have to be careful with the region of convergence. Okay. So, for example, you can now, if you are summing, let us say a geometric number of geometric random variables, let us say x i's are geometric with parameter p, n is geometric with parameter q. Okay. You go ahead and as an exercise you can try finding the distribution of z. Okay. If x i's are geometric with parameter p, n is geometric with parameter q, they are all independent. Okay. Try this exercise, okay, using this. Let's stop here.